Because tree level is where physics is. And so root 2 is a correction of tree level.
At least in the perturbation theory, that's the view. Yes, yes. Yes.
So it's a question.
Okay. So it's a good question.
This question deserves one.
No, actually, these are more than one.
Because these are sometimes when you are students, it's important to have. This one.
But I'll get you one good bottle of cachaça.
For the photograph here, I got here because he was not able to answer this question.
Yes, yes.
And everybody should think on this question.
Yes, yes.
But
I know that
sometimes this means what? This means that there is one empty space in your theory. For this theory, if you have a photon-photon interaction at tree level in your Lagrangian, if your Lagrangian produces photon-photon interaction, you could write that there.
Yes. This thing.
Yeah, if you have this, you could write, for instance, exactly.
Yes.
And this will be plus this one.
Yes. Yes.
Plus, okay, this is a series. Okay, it starts here, page 1, and the other is a series. The action is a series.
Yes.
So, I just telling again, I deserve very much this. and people should think on that because there's a lot of gambles in physics. And so doing by these people from the US, they want to publish the papers. And they do what they want, they think. Then they give the reasons.
Sure.
But if you don't have it, put Newton's law, an apple,
yes.
In your head, okay, apple in your head. Then you can have loop corrections to the apple you have.
Yeah.
But classical mechanics is direct. It's under, okay.
So
I went to.
Yes. So the question was: is there any process which happens only at one loop level and onwards, not at the tree level? I don't know the answer. But I think there are such things because when we said, like, you remember when I showed the perturbation theory, I showed zeroth order as the leading order, which is tree level, and the one loop as the next to leading order, right? The reason why particle physicists don't call them as one loop, two loop, while leading order, next to leading order, is because in some cases the leading order is not the tree level, it's the first loop. So that's why they use a different terminology. Because in the experiment, what we are going to do is, this experiment measures things to leading order, next to leading order, next to leading order. So the leading order doesn't have to start with tree level. It can start with one loop. So I know there are things, but on the top of my head, if you put a gun to my head, which can happen in Texas, right? So I don't know anything. I think this is a good example. The photon thing happens only at one loop. So, I'm not done. I don't know much about these things, so maybe I'll think about it. You two think about it. Try to come up with an answer for the question. Name any particle process that starts only at one loop. There is nothing like tree level thing for that. Right? So that also means it's a very quantum mechanical process. I think you should take 2 more. Okay, so good questions. Good questions. So now I will give you. So far, I just gave you what all I told you.
As a professor didn't want to give you paradoxes.
Yes. Yes, you give to him too. So, everybody deserves a chocolate, right? So for yes.
When the professor didn't answer that, he had to pay.
Yes, it's the price I have to pay for not knowing the answer. If somebody is sitting here on a Friday evening, I better make it worthwhile. Right? They could rather be drinking beer on the beach. So far, what I advertised was some of these processes are important. This is real QCD, and these processes are important in LHC, right? And this is the complication at the tree level itself. And we cannot use Feynman diagram method, although it's very good to calculate simple processes. It becomes very quickly undoable. So we will have to find a new method of thinking about quantum field theory, thinking about scattering amplitudes beyond Feynman. That's the whole process. And I showed if we include in supersymmetric theories, there are some beautiful relations, recursion relations, which can make these impossible calculations finite. Anybody can do this in one afternoon, that kind of thing. So that's fantastic, but that comes at the cost of higher mathematics and supersymmetry, and we have to know so many other things. But this is a process, right? So that's why we have to study this. But that's not the end of it. Our aim eventually, which is open question. Nobody on earth knows the answer for this. Can we use those methods to calculate this? No, right? So can we do that? At least for simple theories, right? So that's the thing. And another thing is, these processes can be calculated in supersymmetric version of these theories using any of that, right? So I don't know any papers on this. Right? So for me, this is true for everybody, right? So you learn physics by teaching and then by writing papers, right? So I would like to give this as like homework for each of you, and then we can publish it. I did that to the colleague, and they said, he doesn't want to talk to me, but they know. So that's too much of a homework, right? So, sure. So now I'm going to list some of the magnetic dipole moment, right? So, magnetic dipole moment of the electron. So this was first calculated by Dirac in 1928 to tree level, and the theory was this experiment. Exactly true according to Dirac's theory, and it was approximately true according to experiments. Right? So this was the case. So when you make a new theory, so the Dirac theory is already relativistic theory of electrons and photons. If you make it a quantum electrodynamics, the first question people are going to ask is, oh, okay, good. Congratulations, you have a new theory, quantum electrodynamics. What can you add to this? So what's your contribution? So that's why the first thing that Schwinger did once the QED was ready in 1948 was he calculated one loop correction to this process. This looks like this. In this case, so at the tree level, at the one loop level, so this is the case, and he showed. So theoretical value was experimental. It was amazing, right? So approximately it's agreeing already to 4 decimal places. This was how many years? 80 years ago? Right? Yes. 71 years ago. This was the case, right? So this is why people started believing in electrodynamics, quantum electrodynamics. Do you know this Feynman's book called QED, the Jewel of Physics? Right? So he has very common, no equations, nothing. And why is it called the Jewel of Physics? Because it's the most accurately tested theory. Meaning if you have a number for the theory and a number for the experiment, this matches to amazing degree of accuracy than anything else in any other area of science. Nothing else. And what is that thing? This is the thing. In QED, this is what they compare with the experiment. This is what makes it so good. So that's why, again, isn't this great to calculate this process at the tree level? We have all the numbers. We can plug in and then get the G theoretically and go see this is equal to 2 and then reproduce this number using one loop corrections to this. Just by doing this itself, you are going to learn plenty of things, right? So until 3-4 loop order is good enough to get a master's. So you're not doing anything new, but just to understand these things by dirtying your hand and calculating things is really good. Okay, so maybe I will write it here, right? It's easier. So that was only one loop. That was 1948. So here I want to demonstrate 2 things. One is how our confidence in the theory increases with increasing precision measurements, and the other is how difficult is it to do the loop calculation. So this is third one was done in 1957 by Sommerfeld. And this is to 2. That's 2. And their value, theoretical value, was
The Sommerfeld is not that one. No?
I'm not sure. Maybe I thought it's the same Sommerfeld as the classical mechanics.
But that one was 1915. No.
Oh, he died in 1915?
Yeah.
Okay, so maybe he's his son. Right? So, but it's a good thing. I'm usually good with the history, but now you're sure that's not true. Right? So, I thought it's the same Sommerfeld. And the experiment, which only came in 1972. Look at that. 57, 72. Already theory is ahead of the experiment. So, again, if you can reproduce this result and then show this is the number using any method in the textbook, that's a fantastic news, right? So you can recognize the names; they are big names, right? By the way, one of my teachers in Texas was a student of Schwinger. He taught the fine structure constant. Like you can calculate the fine structure constant using this thing. So apparently, Schwinger had this as his license plate number for his car, and then when they updated the results, this got a correction, some 137 point something, right? So he changed the number plate to that thing, right? So I have not verified this anywhere on the internet, but I just thought he is right because he was a student. You go check that if that is the case. Right? So that's 2 loop. So now, fourth one. Guess when probably somebody calculated the 4th loop. I mean the 3rd loop calculation, right? So probably when? How long after that might have? Guess any number is fine. Any number.
When they did it?
Yes. See the tree level was 1928. 1 loop, 1948. 20 years later, right? So this is, yeah, let's say 10 years. This is probably
70.
1970. Something like this, right? You expect something like 1970 or something. So this was 1996. 1996. Right.
It's because computer development.
This is because of computers. That's and three loop calculation already this. So this is, so what was the theory?
This remedial,
Yes.
he was supervisor of Silvio Sorella in Italy.
Oh, really? Sorry about the voyager.
Yeah, he was supervisor in undergraduate,
Oh, I did not know that.
undergraduate. After Silvio went to CISA. And Silvio learned the spoon ship. How it was made by through spoon ship. And then Silvio was invited to come to Brazil to be invited to Petrópolis. And he went there and he was teaching us how to play to the school ship. And then now we use mathematics and
Yes.
things like that. No? But at that time, remedial was with the school ship.
Okay. Oh, absolutely. Yeah, I don't know anything about any of these people, right? So, but they are known for something very basic, very important. Okay, so that's that. And then, so that's 3 loop, right? So what about 4 loop? Probably. When do you think this?
2001.
Right? So yeah, that's a good guess. 2006. 2006, right? So by
The people from Siberia, no?
maybe.
No, Kinoshita is Japan.
It's Japanese, right? So yeah. And then again in 2015, the same group of people have done this. Already by the time they do this, they use other corrections, not just QED corrections. They involve other things. So I think so far they have done this. Okay, this is let's say 4 loop, right? And this is 5 loop. But it's not just electron, photon, this thing. They have included other QCD corrections and other things. I don't understand what they mean. But it's still going. So calculating till 5 loop took, yeah, it's 90 years, right? So it's essential. So 2 things we have learned. One is, it's not that easy to go, it's not like a textbook exercise to calculate, go 1 loop higher is very hard, right? It's very hard. First thing. Second thing is, now, if somebody says they have a new theory of electrodynamics, alternating to quantum electrodynamics, which may perhaps explain the say something about the photon-photon collisions and this kind of things, using the same theory, your magnetic dipole moment, if you calculate that, it should agree till all the way here. Right? This has been the problem. There is general relativity, right? So people try to go find alternative theories to general relativity. Sure, so general relativity has produced so many results in the last 100 years. So if you calculate something simple, let's say perihelion of Mercury or something like this, they already died. So the theory is already dead before it's even born. It's dead in the box. So it's very, very hard to come up with any theories. I'm not saying there is no theory. Of course, there is a theory beyond general relativity. There's a theory beyond QED. These are not the final answers. But today, if you come up with a theory, there's a very good chance that it's not correct. It may be good till here. Hardly it goes to this level and then go beyond that. So that's why we have to know that this is what I mean by this kind of thing. So these theories are dead by birth, like out of the box. That's what Nimar Kahneman says. He says like, okay, go do whatever theory you want. Supersymmetry, without supersymmetry, any number of dimensions, include whatever you want, any garbage. If you can come up with a theory, any theory of any of these things, QED, QCD, electrowave theory, general relativity, if your theory is good to like two-loop order, I will get you a position in Princeton. That's what he says. It's just, these things are so tight, so constrained, if you want to just do anything else, it's dead, right? So that's why one should be very, very careful when going into new theories, right? So people just jump into the bandwagon and then start calculating things and publishing papers. It's completely different from solving problems, right? So, and understanding nature. These are like very, very, very different things. So in that kind of theories, you can always publish papers. But you are not doing anything. Yes, please.
I would emphasize, in my opinion, these numbers are less derived from the theory and more from the Kaplan constant. So let's say, what defines these numbers, one loop to loop if you like, is the structure.
Fine structure constant.
This number that is crucial for so what's important to note is that if you have a photon-photon interaction that is not here, they say, okay, everything here is precise, and you want to introduce another thing, probably you're wrong.
Yes.
But just finish. If you have a photon-photon interaction that doesn't depend on the structure function, then you can play. You can play not changing these numbers drastically. And
but that would be very radically different from this thing, right? So if you have a theory which we have Lagrangian for the photon-photon, this thing, definitely that Lagrangian is not only for photon-photon. It should be for any electrodynamic process, right?
like this.
So in that, if you can produce these calculations and show, oh, your theory is independent of the point structure constant, or reproduce this thing until here, forget about like 3 loops, until like 2 loops, 1 loop, because photon-photon process, as you mentioned, starts only at 1 loop. If these standard electrodynamics processes, which have already been there, like for the list I showed, if you cannot calculate, then theory is dead. We should show before that, using that Lagrangian, all the standard model processes that I listed, simple processes, are good till, and they don't deviate from actually measured values, right? That's the problem. That's the problem. So, see, this is QED did so many things. Not just fine structure constant, not just magnetic dipole moment, calculate so many things. Another reason why why these smart people, they still believe in supersymmetry, although layman on the street knows it's not observed in nature, because it does tens of things, hundreds of things, completely different from one another. So it's hard not to take it seriously, right? So maybe I was like, Professor was mentioning about American Journal of Physics. It's like an educational journal in the US. For that, maybe with Aula, I will write an article like 10 reasons why supersymmetry was cancelled, is taken seriously. Why 10 different reasons, right? So, and the last reason, or one of the reasons that probably I will not include, is dark matter and string theory and other things. So there are 10 other good reasons for this. One of the reasons is it simplifies the scattering amplitude. So, but anyway, this is just an idea. Just an idea. So,
Just one,
yes, please.
in the 80s, I was in Cambridge. I was a postdoc there. And Kinoshita gave a seminar.
Wow. You know, so for me, these are just names. But you have a real story about these people or anything. I'm so happy to do
And the seminar, and now I don't remember quite well if it was in true loop by sure.
Oh, okay.
And but I think that it was in for loop,
Wow.
but I'm not sure.
Okay.
But it was in the 84, more or less. So I think that the Kinoshita probably they have before them 2006.
No, this paper that I picked up is from 2006, but he has been working on this for many decades.
No, they have a group there.
Some of them are like, this is, for some people, this is their lifetime's work. All they do is make high precision calculations for magnetic dipole moment. All their life. That's all, right? So they just, and there are people, I will show you this. Since the 80s or so, 3 people, Lance Dixon, David Kosover, and some G. Byrne, these people that they collaborate, all they have been doing is, they're great guys, so it's on the video, right? So it's not like they are trivializing their work. They recently got something called, what's the prize that they got? Some American Physical Society prize for doing this. They have been doing this for like last 40 years. Later I'm going to give you these lecture notes, like what I have. Yes, this is Sakurai Prize, JJ Sakurai Prize. These are the pictures of those people. I put them in the notes, right? So JJ Sakurai Prize in 2014, like 5 years ago, right? They got this for path-breaking contributions to the calculation of perturbative scattering amplitudes, which lead to deeper understanding of quantum field theory and to powerful new tools for computing QCD processes. So they found a new method of calculating the scattering amplitudes. And all they've been doing in the last 40 years is to calculate, like any process that's important for the collider, you tell them this is the process, they will calculate this to 2 loops, 3 loops, 4 loops, something. So they take like 4 years and calculate to 4 loops. Take another 10 years and calculate to 5 loops. That's all. So this is like lifetime work of some people. So many papers I've seen on the magnetic dipole moment. I see this name. So probably he has been working on this since 1980s.
I remember the seminar because English people they like to be they have some humor, black humor. And Kinoshita was there in a very Japanese boring way.
Oh, okay.
Yes. And what is the numbers and numbers? And the people after some time was smiling because it was number plus numbers. But it's a very hard work.
Yes. So
I never forgot to send them out.
Because
it was a mix between the Japanese way and English way.
In India, people have copied like yes.
No, please.
Okay. So calculated.
So far you have been talking about why you should care about scattering amplitudes and so on. But I wonder, where is gravity? Like,
Well, good question.
what is the role of gravity?
Well, where is the Kyle is very, very interested in like quantum gravity. He asked me so many questions about every theory of quantum gravity. He wants to know about every theory of quantum gravity. That's really good. Yes, that's a good question, right? So far, where is gravity, right? So this is like QED. Why? So good. So these three people that I mentioned, right? So let me do a few more advertisements, right? So couple more advertisements. So, first maybe let me list different methods for calculating the scattering. Different methods. The first, guess who calculated who gave a diagrammatic way of calculating the scattering amplitudes first? Right? Fine. So that was in, okay, let me write down the year first. That was the year, exactly. Final diagram for what? That was the year he showed us. Then, in 1986, two people they found a new method. They found some new structures, something related to helicity. Like some of the, it's only like a 2-page paper. You can see that. Maybe they showed there are some nice cancellations if you did something called helicity violation. So they found a new trick for calculating for the gluon processes, n gluon processes. And that method is called maximally helicity violation, MHV. This was the method, right? People use these methods to calculate processes for LHC. This is real thing, not some figment of imagination, no supersymmetry, nothing. This is real, essential. In fact, you cannot calculate, none of the professional phenomenologists use Feynman's method to calculate for the real experiments. This is only for teaching. This is what real physicists use. This one, I mean, for the real experiments. And then, during the same time, 1987, so they found a new method of doing things. Or people call just this as Chinese magic. So Chinese people discovered and people call this Chinese magic. Because why it's Chinese? Because these are Chinese guys, and then magic because it makes the calculating amplitudes so simple, right? So these two methods are extensively used by phenomenologists for processes in LHC and Tevatron and other things. So these are real things. This is probably the first thing you should learn if you want to be a phenomenologist working very closely with real experiments. These are so they develop programs for doing this kind of things, right? So this is taught in textbooks. In principle, you can use this for anything. Only thing is, it's just not possible to do calculations, but it's good. So these are real things. These are just, you can say they are like tricks. You are not doing anything much about physics. You are just inventing new tricks for doing this. These are the tricks, sure, yes. And the fourth method. But by the way, I think this is also another good master's thesis, is to just calculate magnetic dipole moment up to 5 orders and match with already existing patterns. That's, I think, a real good 2 years work, right? So this was my So these are the people who got the J.J. Sakurai. You know the textbook by Sakurai, right? The award is named after him. So they formed something called generalized unitarity. That method is called generalized unitarity. And these methods are used for calculating only the LHC process, like standard model process. You can use Feynman diagram method for gravitation too. Feynman has a textbook called Lectures on Gravitation. He does calculate these things using Feynman diagram, Feynman rules, and other things. This generalized unitarity, 1993, right? So they started this in the late 80s, and they have been doing this ever since. This is their method, and they use this for both QCD processes for LHC and for gravity. And since it's real hard, before we get there. So, by the way, in 1986, these people.
What is with me to this? They use the Feynman graphs or not?
Here, they I don't think so. They don't use the
No.
graphs. No. So they don't.
The ad hoc is just the Lagrangian.
Just the interaction term. So interaction term.
And you're detecting them just.
Yes, and then.
So if you give the Lagrangian,
They will give you the
number.
amplitude number for any order you want. Just order, write to them. Photon process, tree level. They will send you an email in 10 minutes, 0. And then one loop. They may take 1 day and calculate this, like they can do this. So these methods exist, right? So
2, 3, and 4.
yes, yes. You can do all this, right? So generalized method. By the way, one thing, and I want to check. Since Kyle is very strict about gravity,
From my generation, the key to formula was Feynman graphs.
so in 1986, this is an extra piece of information. Right? These people, Mark and so they showed something. So, general relativity, you can calculate, this is done in Feynman's book. This is also a very good exercise. Here's the Feynman rules, everything. To the tree level is good. If you have pure gravity, he showed at one loop there's a divergence. So general relativity at one loop diverges. And if you couple it to the matter, so if you don't have any matter, if it's so it's one loop finite. If there is no matter, but if you couple that to scalar field, that's what Feynman shows. It's divergent. If you couple that to scalar field, but later people showed that if you couple that to fermions and other things, it's going to be still divergent. Any matter. So general relativity at one loop, pure gravity is finite. But if you couple to matter, it's divergent. Here, they showed, taking any arbitrary matter, they showed it is just not possible to quantize gravity by adding matter to the at one loop level. This is not possible. I think they also did the two loop calculations or something like that. It's just not possible. So, generally, without some extra thing, either break Lorentz invariance, add supersymmetry, or something like that. Without that, there is no way you can quantize general relativity. That was 1986. Right? This is true. That is also true if you use this method can be used. This method can be used for pure general relativity to calculate the one loop with matter, without matter, and then show this result is true. This is true. So that's why. So this result is applied in two ways. One is QCD processes, real QCD processes in colliders. The other, that's one branch. That's what they do for getting the grants. Otherwise, they don't get money, right? But that's not really what they're interested in. They want to go do the hunting, right? So they want to go push the front end. So for that, they have been doing something called n equal to 8 supergravity. N equal to 8 supergravity. So this was introduced in the 1970s. Supergravity, which Aula is going to show, and then Caillou keeps asking questions about, oh, if you make the supersymmetry local, you're going to get gravity. Yes, local because it's space and gravity comes, right? So, sure. So one of the reasons supersymmetry was taken seriously is because that gives you gravity, and also it's going to be one loop finite. Whoa, and then people thought, okay, so you made this one loop finite, that's no big deal. Then, again, I'm going to, maybe I'll just make a list here. I'll continue this. So, in 1998, these people, using this method, they showed n equal to 8 supergravity is two loop finite. That was a surprise. Pure gravity is good to one loop, but it diverges at two loops. And they showed, no, supergravity, n equal to 8 supergravity is two loop finite in 1998, using this method. So this method can be used both QCD and n equal to 8 supergravity. Right? So they showed it, 1998. And then, in 2007, they showed this is two loop finite. It's finite in three loops. 2007. 2009. They have some bets, something like, I will not shave until I calculate the next order, something like this. So they will have a weird thing here. Right? So, they showed four loop this goes on. I think as of now, they have showed until like 6 or 7, like arbitrarily, but not like full exact calculation. They have done this to 5 loop exact calculation, but the idea is now the bet is between David Gross and other people in California. They drink wine and then bet both things. So this is now the idea is
And that's why you need string theory to get a whole finite theory.
right. So by the way, this supergravity was born. This was 1970s, right? So that was like 10 years before second superstring revolution. Since these results were not there, although it was one loop finite, but string theory they can show this is finite to any order. This and it's better than that. So string theory practically killed the whole business of supergravity. But now, because of these things, there is a renewed interest in supergravity. Anyway, this doesn't threaten string theories because supergravity is like a low energy limit of string theory. So they're okay, they have the blessings. So these are going on, and then it's becoming a very active area of research. So people are betting probably it's going to be 7 loop divergent. Just an idea, but nobody has done the calculations. So all this is using this method. And in fact, they have a new formulation of gravity, which is basically gravity is equal to gauge squared. So I think Aula would love this. So gravity equal to gauge squared. So they show like graviton propagator can be constructed something like 2 gluons, like fusing 2 gluons together gives the same property as having a graviton. So this is one of the ways to go, right? Until here is not what I actually wanted to talk about in the sense, although I have never done any calculations using any of these methods now, other than just the first method. It would be just a fantastic idea to do any one calculation, like take a process, 4 gluon process, do the calculation in 5 different methods, right? I think this, I always, I like this way of advancing the science. Mine, professor has a different method, different people have a different method, right? So my personal method is, if there's a problem, I want to solve that in just different ways. 5 different ways. Feynman says any good theoretical physicist should know how to solve a problem in 7 different ways. 7 because it's a good number. It's 6, 7 different ways of doing things. I think that's how we make the progress. So all the open problems today, dark matter, dark energy, baryon asymmetry, that's what I've been. Yes. So this is for example. If we just had Newtonian physics, which is differential equations for the laws of motion, we could not have invented quantum mechanics. We could not have got the Noether's theorem and these kind of things, right? So that comes only from the Lagrangian formulation, while the other comes from the Hamiltonian formulation, right? So we're having different methods help this. Same thing with quantum mechanics. So Heisenberg's matrix method, Schrödinger's wave, this thing, and Feynman's path integral method. You cannot start with the Schrödinger's equation, wave equation, and then you cannot go to quantum field theory. Path integral, you can start from quantum mechanics and you can go to field theories and this kind of things, right? So that's why having more formulations of the same theory just makes it richer and then leads to new pathways. So my personal approach is like if you want to solve any of these outstanding problems that people have been trying to solve for 100 years, if you count dark matter, right? It's not by doing dark matter, but by finding alternative formulations for general relativity and quantum field theory. Now you have thousands of experimental results to verify if your theory is correct. Your new formulation should reproduce everything that is already there in the body of work. And then probably it will give you a new insight to doing physics, right? So one of the reasons, so this is my philosophy of doing physics. Learn to do the same thing in several different ways. That's it. So then you make discoveries. You learn physics better, you learn new techniques and all this. And why am I thinking about this recently is because this is exactly doing the same thing. So in Feynman's method, each diagram has unitarity, causality, everything, Lorentz linearity, everything, right? Already, so here you have to do some artificial cancellations, like make it break something, like there is no helicity, break the helicity conservation, these kind of things, and it makes things simple. So this new method, what they are finding in supersymmetric theories is, by the way, Feynman's method is gauge dependent. Meaning, how do we define, how do we derive the Feynman's rules? For example, recently, 2-3 weeks ago, Hela showed how to get the graviton gluon propagator in the axial gauge. That is true only in the axial gauge. If you want in Lorentz gauge, you have to do the new calculation. So, to get the propagator, in order to find the scattering amplitudes, you have to choose a gauge and then do the calculations. So that's a gauge dependent thing. But the amplitude square, the cross section itself, is gauge independent. That's fine. So this is saying there is some sort of redundancy. You are trying to do something which you don't have to do, right? So these techniques, you don't need to know the Lagrangian. This is not the Lagrangian, and you find that. So they are basically using unitarity. They are putting the symmetry first. Unitarity and locality, these things, and try to get the amplitudes without going for Lagrangian. So basically, this research, this line of research, if you want to put it in a more ambitious terms, what they are trying to do is they are trying to find a new formulation of gravity and gauge theories, which doesn't need action or Lagrangian or anything. How about that, right? That's a fantastic way. So that's why I am interested in this thing, because you're trying to do using a new different way. I don't care if supersymmetry exists or not exists. So can I do it in a different way, right? So that's how I want it. That's the method. Maybe it's getting late. Okay, so this is all about this method, right? So this method can be used for both gauge and gravity theories. So that's why I advertise this as both gauge and gravity theories. And also because of this. This itself, what is on this board, is itself one part of theoretical physics. This is owned by these people. They own certain area of the particle physics, the theoretical physics. This is their thing, right? They have been doing this for years. And then this is a whole area of research, right?
I'm a bit confused.
Yes.
I'm saying, for Feynman, the number one, just the one that I know, is one loop to loop to loop. The others, they
are also part of values. Are also one loop, two loop methods, right? So, yes.
You said they use these methods to study QCD, for example.
Exactly, yes.
Do they use these methods also to study the confinement problem, to calculate, I don't know,
any non-perturbative results out of this thing?
effect of that?
Maybe, but yes. So, one of the reasons also, other reasons is to get some non-perturbative idea. Like confinement is a non-perturbative phenomenon, right? So, can they use these methods to do this? Probably yes, but I am not 100% sure. But probably yes. There are a group of people who just use this for QCD, only for QCD and then real. They don't even go anything which has super in it. There is a Superman movie, they don't go to that. Right? So they do just real life things using this method. But the other ones do for this thing, and this has been shown that this is another reason why people like supersymmetry is because it makes gravity all the way to here. First of all, two things. One is it's finite, and also you can do the calculation, right? So that's fantastic. It makes it easy for doing the calculation. So that's the thing. I will list the other two methods, which is my version of proposal is not to discuss any of these methods but only the ones that I'm going to show now. Right? But I think that's not a good purpose, right? Because what's the point in going into that method if you don't know these methods? That's a valid criticism. I am going to take that into consideration, right? So let's use the Feynman's method to do some of the standard calculations, and then later, if you find time, you can do this. But I just want to introduce, there are things there you can think about.
Yes.
So that was in 1993. So this is the fifth method. There you go. So this method is called on-shoe recursion. So again, people use this both for gravity and gauge theories. The supersymmetric versions of QCD and general relativity to do this kind of calculations. That's number 5. And number 6 is this is called this is like some sort of it sounds like dodecahedron, some like amplitude. Do you know a geometric structure called dodecahedron? Dodecahedron is like dodeca is do-deish, like Vinci, right? I think it has 20 faces. It's a regular solid. I think one of the plutonic solids, if I'm not wrong. Right? So it sounds like you are because here the scattering amplitude, the number, is coming as the area of some geometric object in some abstract space. You are finding the area of that. Since it's amplitude and that looks like a fancy dodecahedron, he's calling amplitude. This is Neymarkanian's wordplay. He's young and he's playful and he comes up with these kind of things. And it's catchy and people do it. Right? Britain would never do that. So they're colleagues. So, anyway, so these are the methods. My original proposal was to do these things, only these things. But I think it's no point in just doing these things, right? So let's use the Feynman's method first and calculate for the known processes. And then as we get time, if you don't get time, this is fine. So this is the thing. What else I wanted? So, yes. I wanted to, oh sure, yeah, this is fine. We don't have to go according to the plan. This is fine. You disturb me, you ask me questions, and then, right? So this is for today. So basically what I've done today is, this is a summary, right? So why we should study both gravity and gauge theories together is because if you study them seriously, they're related, right? So you cannot study them separately. And also it's not a good way, it's not holistic. You cannot solve real problems like quantum gravity and these kind of things without knowing, having idea from both the things. If you really want to go there, you have to know both. You cannot just escape from knowing one of the things. That's good enough for many people make careers out of it. I'm not saying it's wrong, but you cannot just study quantum field theory and then go solve a problem in quantum gravity. Impossible, not possible, right? You have to study together. First thing. Second thing is why we should study scattering amplitudes. Because if we want to go beyond the standard model, any of the things, any new physics probably is hiding. The signal of that is very small. So for that we have to extract, take away all the backgrounds. So in order to know that, we should know all the standard model processes to very high precision. And I showed you using different things. One for the magnetic dipole moment. How difficult is this to, just by looking at the numbers, like the years, the dates, how long it takes to go one loop order higher, right? And also use for the QCD processes, it's difficult. Then I showed you different methods for calculating the things in the literature, and one of them is so recent as 2013. And this is used only for n equal to 4 super n-ings. This is not like Zwiebern, Dixon, Kosover's method. This can be used for. This is not been used for gravity. If you can show that, you can use the amplitude hedron calculation for gravity, supergravity, n equal to 8 supergravity. That's fantastic. So far, it's only for this thing, right? So there are open questions at all levels. You can pick and choose whichever you think is appropriate for your time, worth your time, and we can talk about those things and work on those things together, right? So that's all I have to say for today, right? I have a lot more material, but let's stop here for today. You can ask me any questions. Any questions?
You are leaving this course this semester or is for the next
So
semester?
the original point was, first I wanted to give this course at Wish, but again I told them late, nobody registered for that. But Halal was very excited. Oh, this is really good course we should do. I told him, where should I know? Then he said, oh, let's do this at CBPL. But again, we have to go through some bureaucracy and this thing. By the time they announced, already like everybody had taken so many courses. So Halal said, like, we'll share our course. But he has to finish his what he wants to do too, right? So like I am getting chance whenever he is busy with something. So I am just like sneaking in these new ideas. And probably I will not be giving this like a full-fledged course this semester because there is no time here. Like everybody is taking like, hey, how many courses are you taking this semester? 3. That's too much, right? So because everything I go, he's there. I go because I can go, but you should be busier than I am, right? So and this is too much courses, right? So whenever I get chances, like I will introduce some new ideas. But today all I did was, there is something we can do, right? Something that nobody is doing here in this country, right? So we can do it. So, do you have anything else? Do you have any other things to say? So you are saying, instead of doing all this fancy cluster theory n equal to 4 super n-ings and other things, let's just do the Feynman's method for the standard models first, right? And then in one class I will do that, next time when I get a chance, and then we can do other things.
I have a model to be non-linear electromagnetic to do with photon-photon interaction.
Sure.
And then that's perfect well the importance of to start the photon-photon amplitude, you know?
Yes.
So I'd like very much to follow your course,
Sure,
to
yes.
learn
So yeah.
work together that.
Have you done any of these calculations already in the theory? Like, have you calculated, let's say, electron-photon cross-section or something? So it would be a nice thing to do those, right? So,
Yes, the model is still working with the Lagrange and
okay.
information laws, all that thing. And the next step is to calculate amplitudes and the great number.
I have 2 more. Do you want one?
No, for me, not.
So,
Thank you.
okay, let's call it a day. Obrigado. I will try to write down everything I told today and give references for these things and then give it to you guys.
It's good because we can publish in the Professor Global.
Sure, okay.
And then people around Brazil can.
Yes.
The important to have public.
Yes.
Pode.
Yes,
Tem outro?
Do you want one? take 2. So, I mean, here you can ignore all the things.